Well, it's a great pleasure, a great honor to be here. Now I realize this is a very long session. Some of you were clearly hoping for a break. And it's a very tough act to follow. But I'll try to keep you entertained, and maybe you'll even look at some of the appliances in your home in a new light after I'm done talking. So before I start, let me thank the contributions from Vincenzo, who did part of this work with me while he was a PhD student at Imperial College, where I used to work, is now at EDF R&D in UK, where we have a collaboration with, and Nathaniel and Goran, who are helping with the practical implementation of that now. This talk really is coming from the application perspective and went into the mathematics from there. So you already heard this morning in Dario Bauso's talk mention of frequency and swing equation. Let me just kind of give that a cartoon footing, just so everyone here knows what we're talking about. So we are running on an AC electricity grid with a nominal frequency of 50 hertz, right? So what happens with the grid is that we have generators, often big machines, sometimes small solar panels, injecting power into this grid, and we have appliances and large machines consuming this power at the other end. And in the middle we have a little bit of energy stored within the grid itself. And this energy is stored within synchronous rotors of the generators. And they're spinning, I'd say 50 hertz or any other frequency that happens to fit. And what that means is that the kinetic energy that's stored in these machines by spinning is proportional to the rotational speed squared, so the frequency squared. Plug in your favorite constants over there. Now then, to a first order, the grid, let me just stand here because then everyone can see my hand. So the derivative of the grid frequency is proportional to the mismatch between how much power is injected and how much power is extracted from the grid. And that's been a great boon because that gives us basically a free control signal, right? We get a measurement for the mismatch through the frequency. But it's also something we have to watch very carefully, because if you are a grid operator, and we have at least one here in the room, then you need to make sure that this grid frequency remains very tightly around the 50 hertz band. So you have a little bit of time once you notice a mismatch to go and correct it, and that's the balancing challenge that the grid operator has, right? So watch the grid frequency, make sure it doesn't exceed this narrow band of 0.2 hertz either way by changing supply and demand to match each other. So currently, if you have a large credible loss in the UK, that's Sizewell B nuclear station of 1.3 gigawatts, you have about 10 seconds or so before you need to have really done something significant to make sure this frequency doesn't sag out of control, right? So you lose a large power station, energy has to come from somewhere, comes out of the spinning machines, and then the grid frequency starts to slow down. So to not exceed this limit, you have to be quick. And another development is that inertia is decreasing all the time through renewable generators that cause this decay time constant to go down. So you need to act more quickly into the future. Okay, so that's kind of the 101 electrical engineering bit here. So who's supplying all this flexibility that we need to balance things? Now, historically, pointer doesn't work. So we've had this grid with large generators supplying power. We get these new renewable generators, and the energy went to our homes and our factories. But really what we're seeing now is we get this bidirectional flows with batteries, right? We have the ability to store some energy and use it on short notice. And we are able to use responsive loads, modulate the energy demand by our homes and our factories, our machines, to help in this balance, addressing this balancing challenge. So quickly, kind of giving you this high-level picture of types of flexibility that we can be addressing is kind of from large to small, from large flexible generators where we have very few of, but give us large chunks, all the way, and I'll be a bit quick here, all the way down to the residential bit, right? The residential demand response, where we have very, very many, very small units. And that's what I call the long tail, right? So there's a lot there, but it's hard to extract it all. But that's what I'm interested in, how to use the flexibility offered by people and their appliances to help balance the grid. So that's a long-winded introduction. Now, the outline of the rest of this talk is as follows. So I'm going to talk about refrigeration, how to use refrigeration not because it's necessarily the only thing we can use, but it's a nice example where we built some nice theory that helps, but that may be able to extend to other areas. How we control that, and then extend it into a broader discussion to see how we may be able to use these concepts differently. And finally, in the context of this workshop, I present a toy model that might help get some of the mathematicians more involved in some of this work. So I apologize to people who have seen me speak before. I think the first 2 bits you might have seen, but I hope to add some new thoughts towards the end that are also of interest to those people. Okay, refrigeration, why? Refrigerators, we all have one, and the nice thing about a refrigerator is it provides its service through its energy consumption, not through its power consumption. So what I mean is by that is that if you look at the fridge, what it's doing, right, so this is time. The main power consuming component of a fridge is the compressor. It typically switches from on to off and back again. Right, so here it's off for a while, it switches on, consumes some amount of maximum power, then switches back off, back on, etc. Right, so it modulates the temperature up and down, as you see over here, by doing so. Right, so when it's on, it cools down rapidly, then slowly heats up again. And that's how it cycles. Now the fridge doesn't particularly care whether it consumes power in this very second or maybe 10 seconds a few minutes later, right? So it's flexible in that regard as long as it's consuming the right amount of energy for cooling on average. So that gives you flexibility. It gives you flexibility to move these peaks backward and forward in time as long as you stay within the permitted temperature bands. And just to say, I'm using fridges now, but fridges could also be other thermal appliances. You can apply the same thing for the pumping element of gas boilers, etc. Right? So it's all thermal or thermostatically controlled loads are similar. Okay, so refrigeration. So why? Okay, that's one fridge. We can shift something. So why is it interesting enough for us to be looking into? Well, the opportunity is quite large actually. If you look at all the fridges, and again, I should still update my numbers to get these numbers a bit narrower. But you get about 2 to 3 gigawatts of refrigeration load in the GB island system. And depending on the time of day and the time of year, that you're looking at kind of 5 to 15% of system load. So that's significant, right? And that's always on. That's the second bit, right? So it's always on, it's always there. So this little green kind of is just a sketch, right? So don't take this for the camera as well. Don't take this as my promise is exactly that much, but it's roughly that green layer over there is flexible stuff that you can move backward and forward, and you can use that to run your whole system more efficiently, right? You can use that to not run this extra generator in reserve in case something goes wrong, right? You can rely on the fridges to help you out for, tide you over for 10, 15 minutes while you start up a new generator, etc., right? So that's there. And it's free in principle, right? It's free secondary use as long as you don't interfere with the cooling. Of course, people might want to get paid. That's a different issue. But in principle, the fridge is on, is there. If you can use it, why not? Of course, the challenge is you have to make sure the fridge remains a fridge, right? So don't mess with people's cooling performance, because then you won't have the service for very long. Also, make sure this is robust, right? This idea is that you're going to control millions of fridges. So it needs to be robust, it needs to be very scalable, it needs to be cheap. And finally, you need to have precise controllability. So one of the things that you quickly realize if you do this in a kind of hand-waving manner is you quickly end up with solutions where you synchronize all fridges, right? So you tell them, okay, all off the grid now, please pause. And then 15 minutes later, they'll come back, right? Because they get warm. And then you get this huge swell of fridge power consumption. So that's a bad solution. So it's easy to get bad solutions, so you want a good solution that you can control. So that's our list of demands. So the general approach that we ended up coming up with is something that, goes by various names now. We didn't name it, so one thing I learned is you should always name your model or your method, because then you get cited and talked about a lot. We didn't do that, but now I'm calling it distribution-referred control. And really, it's somewhere, typically if you read about demand response, then people take one of these two approaches. So on the one hand, you can say, well, I'll take indirect control using incentives. I'll send out, broadcast a price to everyone, and people can see, or their appliances automatically can see whether they want to change their behavior according to this price. Or, on the other end of the scale, we have this big central optimizer that receives state information from all appliances throughout the grid. then runs an optimization and instructs every appliance when exactly they can turn on and have to turn off. So this is great because it's super controllable. You can do whatever you want, but people may not like it, and you are really dependent on real-time communication. So we're trying something in the middle in a kind of a mean field sense, and that's why it's being presented here. So our requirements are we want to control the aggregate power consumption of heterogeneous collection, large collection of on-off appliances, right? So this is, the power consumption is the sum of the power consumptions of the individual appliances. That's the thing we want to control. And we try to use a single global control signal that I call pi, where pi is defined such that the value of 1 means nominal power consumption, right? So that's do nothing. And then a half means half your power consumption, and value of 2 means double your power consumption, right? So that's your signal. So in such a way that the power consumption is the nominal value times pi, right? That's the aim. So that's a simple thing once you have the controller in the back end. And appliances, we keep in mind that appliances have limited controllability, right? So they are on-off appliances in this case, and they have strict temperature constraints. So there's limits to what you can do. So this is the picture, right? So we have this signal pi. We send it into a bunch of fridges. They are on and off in various ways, such that the sum of the power consumption is proportional to this control signal pi. Right, that's the aim. Of course, the issue is, and this is kind of a rough sketch, you have a heterogeneous set of appliances. They might all have different temperatures and different temperature ranges, right? So this is kind of roughly the space of thermal models, right? So a fridge doesn't really move between these, right? So the fridge, well, it might slowly move between these. If you load it with a crate of beer, you, for all intents and purposes, for the grid, you have a different fridge, right? Because suddenly you have a very slow fridge rather than a fast fridge. And this is the space of its internal state, right? So that's temperature, whether the fridge is on or off, etc. Right? So a fridge at any point in time sits somewhere here or there, right? So that's the location of your fridge. And of course, these bounds up and down are very important because here is, for example, high temperatures should not switch off, and here, low temperatures you should not switch on, right? But fridges, we don't want fridges to start talking to each other or to a central entity, right? So they need to somehow incorporate this knowledge that there exists fridges that can't switch on and that can't switch off, even if they themselves are not affected. So what we do, we design this control strategy based on all states for a specific model, right? So we say, okay, well, you're a fridge. Let's assume you can't talk to anyone else. You don't even know which fridges are out there. But we assume that as a fridge, you can know your own model. There are issues with this too in practice, but let's assume this for now, right? So the fridge knows its own model, and then says, okay, well, design your control strategy based on all the states permitted by your own model, right? So your fridge with your settings, your owner likes to keep it very cool, right? So you can be between these and these temperatures. Let's keep that in mind. So can we do this without real-time communication? And then we do that for every one of these fridges independently. So the way this works, and this is in progress every time I make a few changes. So we kind of went backwards, right? So we made this work and then tried to find how it works. But then this is one step. So let me walk you through this quickly. So the expected power consumption of the population as a whole, right? So we look at a large population of fridges, is the expected power consumption of that population given the control signal, right? That's for all times past, right? So we can't look into the future. We don't know what's going to happen. Now, we say, okay, for this population, right? So we have this population that has different states and different models, right? So we call this M and we call this S, right? Model, state. So we say, right, so these are N fridges. Let's say I know N, right? And let's look at the expectation of an individual random fridge, right? So that's its power consumption is PA. But it's PA given a certain model, and what happened? Sorry, let's start here. The expectation over all models, right? So we take the expectation over all models and the expectation over all states given that model and given the control signal that happened. So that's kind of just breaking down the expectation over its two axes over here. Now, the expectation over all models, we know that we have exactly n fridges with different models, so we can just sum over them, right? So there's actually a discrete set. So we can take an expectation over the finite population, so that's just this sum over here of the expectation over the state for each model. So these nicely cancel out, and then we get with this sum, right? So we say, well, the expectation of the total power consumption is the sum over the expectations of each fridge given its random state, right? And it might have random states because it was initialized differently, right? So I switched my fridge on 3 years ago on a Sunday, 5 o'clock. If I'd switched it on at 7 o'clock, I would have been in a different state, right? So that's essentially the uncertainty you're taking the expectation over here. And then we try to design it in such a way that this expectation is proportional to its nominal power consumption driven by the control signal. And I'll get to some more details later. Well, actually, they're in the paper, but yeah, bear with me for now. So this is the idea. So there's 2 steps here. One, we say we design this controller in such a way that its expected power consumption is proportional to this control signal we send. And 2, we know that all fridges are independent because they can't talk to each other. They only receive. So they're conditionally independent on the control signal they receive, because that's the only thing they use to interact with the outside world. And then if that's true, this follows. And therefore, well, this is the nominal power consumption of all fridges. And then we have our desired behavior. OK. So that's the idea. So every fridge should act as a population of itself in different states. And I'll show you this in specifically later. So back to our control spectrum, that puts us somewhere over here. So this distribution referred control means that we have collective goals that are set centrally, which is this pi control signal that's broadcast to all the fridges, and then the fridges individually act on the basis of this. And they act semi-autonomously. They don't need real-time communication. They can actually make their own local decisions, and that will hopefully become clear in the next 15, 20 minutes or so. Okay, so let's make this very specific now for these fridges, how this is done. So let's start here with the refrigerator dynamics, right? So this is the dynamics of a single fridge. We use the simplest possible model, right? So we have one cabinet with a compressor that can extract heat from it if it's on. And we have heat coming in from the environment, leaking in from the environment all the time. Right, so that's our 2-state model, where the temperature changes as follows, right? So it either relaxes to the ambient temperature if the compressor is off, or it approaches some asymptotic T on, which is usually very cold, if the compressor is on. And you won't leave the compressor on all the time because it freezes. And then what you see is this behavior, right? And it switches usually as it reaches the upper or lower temperature boundaries, right? That's the regular hysteresis controller that you find in your usually cheap fridge. Taking this and integrating this and looking at this from a steady state temperature distribution, you get the distribution that's seen over there, right? So this particular fridge has a minimal temperature of 2 degrees, maximum of 7 degrees. It has a distribution that's then between these 2 temperatures, and you can compute the shape of this distribution exactly for this simple model. And we'll now interpret this as a probability distribution, right? So we say if we pick a random fridge of this model, and we don't know when it was switched on, right? So let's just, we pick one. It will be somewhere in here, and this is the probability distribution for the temperature of that fridge. Right, that's step 1. Now, you can kind of go through the model equations, and it follows that actually there's a really nice simple equation that relates the rate of change of the average temperature of that distribution and the power consumption. So that's really nice. So we now have power consumption linked one-to-one with the population average temperature. But actually, you'll notice that the population average temperature really underspecifies the population as a whole. So we have many possible ways in which we can start playing with this density, right? So we just kind of take the approach that, well, let's play with the density. And there's many ways in which we can do that that all lead to the same change in population average temperature, right? So they all correspond to the same change in power consumption for this population. So actually this gives us freedom. Right? So we can pick a nice transformation that gives us the properties we like. And this transformation, is basically plumbing physics over here, right? So continuity equation means that we try to continuously change the temperature distribution of these fridges, and single fridges can't jump from one temperature to another, right? They have to continuously move between one and the next. So we're looking for continuous transformations of this distribution. And we pick a simple one-parameter family of distributions that is compatible with temperature limits, that's sufficiently slow that we can actually do it in the fridge, and that has a known distribution at all times, and that's this thing over here. Now, instead of trying to let you understand what this is doing, it's a simple compression. We just define, out of all possible transformations we could do, we say, well, let's pick the simplest one. We just compress this range of temperatures, right? Between these two limits, it can never exceed the limits, so we got that sorted. And then we just compress it either one way or the other, depending on whether we want this average temperature to go up or down, right? And then in this way, that's a sufficient way of doing it. It's not perfect in any sense, but it's easy and it's sufficient. So then that brings us to a point where we flip the problem on its head, right? So we said, now we have a population of fridges where we know if we can make this population do, or this, well, population or this probability distribution do a certain thing, then the power consumption will change the way we want it to. So then how do we actually get the individual fridges to do this to their population, to their temperature distribution? So let's start here. We have our desired power response. We transform that into our desired population behavior. We then say, okay, well, this population behavior, really, an individual fridge can only really have two behaviors. In our case, it can be on or it can be off, right? So this population, if you see a certain net velocity here of fridges of this temperature, let's say all fridges of temperature 5 degrees, right? This flow of probability density is such that the average flow speed is, let's say, +1 degree per half hour. You can say, well, actually, we don't have any fridges that can do +1. We can only have fridges that can do +2 because they're off, or we have fridges that can do -10 per hour because they're on. Actually, so you can compute this backwards, and you say, well, then I know what my populations of on and off fridges are in here. And then, because I know this distribution of on and off fridges, and I know how they change over time because I compute this from, oops, I keep tripping here, from this desired power consumption, I can compute the required flux, right? So how many fridges are supposed to be switching from on to off and from off to on? Once I know that, I can say, I'm nearly there, because then I can say, well, actually, so this particular fridge currently has this particular temperature, right? So there's a certain rate of change, a rate of switching from off to on, let's say. So let's suppose I have a fridge that's currently off and it's at 5 degrees, so it's here. There's a certain rate of switching, and I can then randomly see whether I happen to be the fridge that should be switching on or not, right? So you draw the random number and you switch stochastically. And if you do this consistently, you end up with your right distribution. Okay, so more details in the paper as ever, but yeah, that's the short version of it. So, summary, every appliance knows its own state and its own model. It forgets about its state for the moment. It uses the model first, right? So it says, okay, I'm a general fridge of this type, right? My on and off temperatures are such and such, but I forget at the moment whether I'm on or off or which temperature exactly I have. Then constructs this homogeneous virtual population of all fridges of its type. Then manipulates this population in such a way that it has the desired characteristics in probability. And then computes backwards for its own particular state how it should be switching to achieve in this population the desired behavior. So really it considers itself as a random representative of a population, and then it takes actions in line with what it wants the population to do. Yeah? Yeah.
There is one point which I don't understand. The signal that you're looking for is pi of t.
Yes.
And I have the impression I don't understand if pi of t is the same for everyone. So
It is.
So I don't understand the last point.
Which one? 4.
Because you have to design pi and it is the same for everyone.
Yes. So
Random.
no, there's two aspects of it. No, so pi is the same for everyone. So there's another aspect. You have to make sure that you pick a pi that's achievable by all. But let's assume that's another story. So let's say pi is achievable. Then, because every device will construct a different population, right? It has a different model. It will construct a different population. But it will say, well, for my population, fridges that have temperature X should do this. But then another fridge has a very different population. It might have a completely different kind of slope here, shape, anything. Right? You can do this for fridges and freezers. Freezers would be sitting over here in the negative temperatures. Again, very different. So yeah, everyone would basically we do a different computation. So all this happens locally. So the pi comes in, and then the fridge does all of this locally. And then it has the property that in probability, the average behavior is as you desire. So this is kind of an example that I've shown too many times. I should come up with new examples, but this is an example where we look at 20 fridges doing this switching in response to this signal. So there's a dotted line over here, this pi. So it starts out at 1, then drops, and then kind of has this, kind of low period where it reduces power consumption for a while, and then gradually has a recovery built in, right? So there's this signal. So we have 20 fridges tracking this. You see their individual switching behaviors, kind of low being off, high being on, right? And it doesn't look like much, but if you add 1,000 of them up, you see this kind of, this shape really nicely coming out. And if you go to kind of 100,000, I haven't done 100,000 here because you can't see the line, because it tracks it exactly, at least within fluctuations. They get smaller. So this works. That's nice. This is also now something we're doing in the lab. So this is the pictures by a master student, Annabelle Henry. And again, this is this fridge we're now using with EDF R&D in the UK to kind of develop this a bit further and see all the ways that this can break. Mostly, there's a lot of real life fridge stuff that comes in that you don't really know in the beginning. For example, here you see the 3 temperature sensors at the top, middle, and bottom of the fridge having completely different temperature behaviors and huge temperature differences between the top and bottom of this admittedly very, very cheap fridge. So these are things you have to think about to doing this in practice. So that's where the lab really helps to kind of take your theoretical blinkers off sometimes and see what needs thinking about. But that's work in progress. Now let me make a few more general comments on this type of controller where I think it's really interesting. So this is a particular example for fridges. But I think it's the power of this approach sits, I think, in a few particular aspects that might be more general. So one is what I call its kind of ability to operate semi-autonomously. So what does that mean? Everything I've talked about so far is about this arrow on the right. Right, so we assume we have some kind of aggregator, which might be the system operator, might be commercial aggregator of some type. And it sends this real-time control signal pi to all fridges, right? But if you recall in the beginning, we kind of have a free control signal. We have this frequency, this grid frequency that we can measure as well, right? So we can also use that as a control signal. So we don't need to actually send in real time a signal to millions of fridges. We could use the grid frequency in the fridges to kind of have a built-in power response model. If frequency is this, do this. So this can be adapted, this can be changed over time, but kind of in a response design cycle, right? That doesn't need to be real time. This can be hours, days ahead, right? So you can update maybe for grid conditions a few times a day. You could do that. So that's low latency interaction. And in the meantime, you have this, you need to occasionally close the loop because the aggregator, that's what I quickly mentioned before, the aggregator needs to know what the fridges can do. So there's also kind of papers on that. another talk. But yeah, you can communicate back to the aggregator what these fridges can do using such a control. But again, that's slow. But then operationally, in real time, the fridge can take its own actions, right? So if the grid frequency suddenly changes, it can react. If suddenly I open the door and the fridge gets warmer, it can react. Although, admittedly, that's not in the theory yet, so we have to see how that affects the results. But so that's the operational cycle. It's much faster, so you measure the temperature, you potentially update your model, and you switch on and off if necessary. And then occasionally, yes, you need to communicate back to base, essentially, if all models have changed significantly, because, for example, it's no longer winter, but it's spring, then you have a different collective unit on your hands. Okay, so that's kind of the principle. It's semi-autonomous. In real time, it's autonomous, but at longer time scales, you have the possibility for interactions. So what are the underlying principles here that make this work in this way? And this is work in progress. I've been talking about it with various people in the audience for, I think, 2 or 3 years in various forms. Still haven't quite pinned it down, but getting closer. So one is it's fully decentralized, right, in real time. So we have this single broadcast control signal that can also be generated locally if need be. Because they don't communicate with one another, and we'll get to exceptions in a minute, the device states are also conditionally independent. So they're independent, conditional on the control signal they have received, because they all receive that signal, act in response to that, but otherwise are not synchronized to each other. So if they start out independent in some sense, then they remain independent in that same sense. Second is that it is unbiased and is consistent, right? So we have the right expectation value, and we have, as n goes to infinity, as we get more appliances, we get closer and closer to the desired answer. So that is nice as well. And finally, I think then this one is really, really important, because these two are not sufficient, right? So you can have these two properties, and then by sending lots of different signals, send each fridge into its own corner of its state space where it can't move anymore, right? So we have this third property where it's globally reversible, right? So if we send out this pi signal, which kind of has this big dip, right? So we tell it reduce power consumption for a while, and then later on we recover by the right amount, then all fridges will be back in their steady state distribution again. So they will be fresh to use, right? And that is really important. So basically, this gets you a more general type of independence, and I'm looking here at the mathematicians to kind of help me sort this out maybe in greater detail, right? So there is a more general type of independence on longer time scales here. And finally, this particular implementation is memoryless, right? So we don't work with schedules. We don't compute an optimal schedule that says, right, given your temperature now and given this control, you will switch off in 5 minutes and come back on in 35, right? We don't do that. It's every, sorry, that's the wrong wire. At any time, it takes actions based on its current state and current temperature only. So if that changes for some reason, because I've opened the door or something else, then it can just adapt automatically. So I think that's very powerful. So that's that. Now, in the context of this workshop, let me use a few minutes. I think I have 10 minutes left, maximum. So I'll be quicker than that. To extend this to something, so this is clearly kind of a mean field-ish approach, right? So we send in a deterministic signal, we have lots of fridges, and out comes something that is stochastic, but on average, in expectation, the thing we're looking for. In some sense, that's still a bit of a boring mean field. I guess when it gets interesting is when you consider this feedback loop, right? So when you consider the fact that these fridges, let's say I have many of them, are used to actually regulate the grid frequency, right? So then, and let's say they respond to the grid frequency too, right? So we have some external stochastic demand, right? Some external mismatches in demand that generate some stochastic signal for the fridges to follow. The fridges respond, but they're not infinitely many, they're just many. and their response is also stochastic, and that in turn influences the balance of the grid, right? So we get this feedback loop of these stochastically responding fridges. So what does that do? And especially, this is just a question I'd like to pose. Can we rely on on-off loads like this to balance a microgrid, right? So when we're talking not millions, but we're talking maybe thousands, does this work? I'm not sure. It's an interesting mathematical problem, but to get mathematicians interested, I made this toy model. Now, when I thought about telling you all about this, I thought I'd have lots of time to run examples and do things and show you great results. I didn't do any of that. So I'll take this in the spirit of a proper workshop. So I'll just give you the model that I kind of doodled up. And if anyone wants to sit down with me and talk about it, work on it, then happy to do so. So kind of a toy model that's slightly less complicated than the full fridge model, because that always takes hours to explain. So let's think of something simpler. So we say, let's take we have an elementary device model, which is just a complex circle state, right? So we have a state time of function of time that evolves with some fixed velocity. Might also make that stochastic if you want to, and some random offset, right? So it just spins around, right? That's your spinning thing. So that gives you your the important property in fridges, your persistence, right? So they have this persistence property. They can't just switch on and off and on and off, right? So they go through this cycle. And there's a period of 1 over Vj, and it has random initial conditions, right? Let's assume that. And then in terms of power consumption, we say, okay, well, the power is, this is a kind of an on-off function. So it's either P max or it's 0, right, for that device. And it's P max if this one is true. And true means that if the angle, phase angle, is between two to be defined angles, right? So if it's in here, it's on. If it's in there, it's off, right? That's kind of the simple toy model here. And then somehow we need to define these cleverly, and I can talk more about that, but not in the 5 minutes I have. So that this difference is proportional to, well, the steady state duty cycle, right? So how much the percentage of time it's typically on, and then multiplied by this control signal pi, right? So that's over here. So that's kind of a simple model. So we have lots of independently spinning machines that are on or off depending on where they are in their cycle. So this has the same properties where the internal state is independent, mutually independent. So that's nice. So that kind of captures that basic behavior. So clearly we can consider this as a stochastic system, right? We can look at one unit. So one unit now becomes essentially, well, its power consumption is P max times a Bernoulli random variable, right? So it's either on or off. And the expectation is therefore exactly the right thing, right? Because it spends this proportion of time in its on zone as designed. And then as a population, we take the sum over all of them. And remember, we might have different power consumptions in each, and we might have different natural duty cycles in each. We get that the expectation taken over all random initial conditions, right? So that's just U. Again, gives us the same desired answer. So that's, again, by design. And in distribution, if you get lots of them, we have some central limit theorem that we can apply, and we get this, right? So we get our expectation and our variance over there if I didn't make a typo. I'm sure you'll spot it if I did. So that's kind of the simple model. And then tying this all together is well, putting it into, question, what's the time dependence of this thing, given that they all have this persistence? I don't actually know, right? So the spot behavior at a given time t is fine. That's the central limit theorem, but what's the temporal behavior of this signal? I don't know. Maybe you do. Maybe you can make a good approximation of it. That would be nice. And then putting this into a system, well, here's our old friend, right? So for the evolution of the frequency, we take the fluctuations in the fridge population and all external deviations, which basically become common noise, right? This is all common noise to all fridges. But we have this. I see previous for more details. And finally, we can say, well, okay, we could build a simple droop controller, right? So we could say, let's just let the fridges respond in proportion to the detected frequency mismatch, right? So any change, any deviation between the desired frequency and the actual frequency, let's respond proportionally as a first step. So how does this behave? I don't know. That's an open question. Under which conditions of n, the number of devices, alpha, beta, the noise, and the velocities, what happens in this system? Would be fun, I think, to look at it as a simple example of this kind of control. So that's my gift and/or question to you. I'd like to see what's in here. So let me end then with saying that we came up with this distribution referred controller for refrigerators in particular. That's non-disruptive, meaning that it doesn't interfere too much with the temperature dynamics of each fridge. That's decentralized and it's accurate once you have large numbers. We think it's appealing to kind of generalize this to other appliances, other types of loads, perhaps. And we are currently looking at further developments in this. So these toy models, I think, are really nice to get some mathematical insight. That goes over my head and my capabilities. Simulations we're developing to kind of look at sensitivities to misspecification, right? So what if a fridge thinks it has one model and it actually has another model, right? You get interesting things. So this all depends on some truth being out there and being correct. We do these lab experiments to meet the harsh real world in hard ways. And finally, we're looking at optimal control, right? So if you get all these devices, I haven't talked much about that, but if you put a lot of these devices together, you get something like a leaky battery unit. There's various kind of models for this going around. But once you have a leaky battery unit, how do you actually control it, right, in aggregate? So there's two levels, right? So we're looking at the low-level control. How do you control the fridge? But then once you're an aggregator who has, let's say, 100,000 or 1 million fridges, how do you control them, right? So how do you send this pi? How do you construct pi to be beneficial for either the system as a system operator or to be beneficial for your bank account if you're an aggregator? So these are questions out there. Happy to take other questions from you as well. Thank you.